Hey, I think we got a quorum and I think we got the recording started. Welcome back for another semester of Friday seminars here at UTIG. I'm delighted to introduce Peter James from Baylor. Peter is a associate professor at Baylor working on problems relating topography and gravity in the terrestrial planets. Peter got his undergrad from Brown and then a PhD from MIT, and has been a member of the Lunar Reconnaissance Orbiter Science Team, the GRAIL gravity mission to the moon, as well as the MESSENGER mission to Mercury. Today he is going to be talking about Venus.
Thank you for the invitation to come speak. I'm sure some of you are more familiar with this than others, but this is an exciting time in planetary science, especially for geophysics. We have Europa Clipper safely off the launch pad, and there are several people here who are involved with that mission. There's the InSight lander on Mars. That's the first seismometer on another planet. And then there's also a CLIPS mission on the way to the moon right now that will do magnetotelluric measurements. So magnetotellurics is a method that's growing in popularity on Earth because it has very deep sensitivity, like hundreds of kilometers. And that lets you see lithosphere scale conductivity of the subsurface. And so yeah, that's the Lunar Magnetotelluric Sounder. And even if it ends up not being much more than a tech demo, I'd call that maybe the most important geophysical lunar lander in the last 50 years. So that's on the way to the moon as we speak. So lots of exciting stuff. And of course, launch costs are going way down in recent years, surprisingly quickly. Mass payloads are going way up. So the next few decades will be a wild time in terms of the instrumentation we can get on other planets. So I wanted to start off with a poll. I'm curious for feedback from this audience. What do you think is the reason that NASA should be exploring space? So there are a few options, and there's no wrong answer, but one reason you could say is to understand the formation and evolution of planets. Another reason could be life. So the mantra for NASA, for at least the Mars program for a while, was follow the water, because that's the search for microbial life, essentially. Aesthetics, it adds beauty to society the way that art does. People are really inspired by exploration and seeing new worlds. In terms of resources, that's why we are interested in asteroids and the moon and cislunar space. Geopolitics is another really valuable aspect of the space program in the 20th century, this cooperation between the United States and the Soviet Union, and collaboration in a way that was really positive for promoting peace between the two nations. And in the future, that will continue to be an important one. And what did I leave out? I think I got everything. So yeah, these are all good reasons to study planets. I'm not surprised that this group has a strong emphasis on understanding the formation and evolution of planets.
What's your read?
Yeah, that's the one that I would go with, and I'll explain why. So, I think this is one of the underrated reasons to study other planets, that we have precious few rocky bodies in the solar system that are comparable to Earth at different stages in its formation and different regimes. And meanwhile, we are seeing lots of exoplanets, including some that are starting to be Earth 2.0, or branded as such. So when we are looking at planets around other stars that are similar distance from their suns, similar sizes, do we know that those are going to be Earth-like, or are they going to be something else? So in terms of comparative planetology, in our solar system, I want to ask which of the planets is most similar to Earth? And it probably comes down to Mars versus Venus. But in terms of size, Mars is much smaller than Earth. Venus is closer to Earth in terms of distance from the sun. It's about the same gravity, about 9 meters per second squared instead of 9.8. It's made of some of the same materials. So the Soviet landers found basaltic compositions in the lowlands of Venus, and those were derived from a peridotite mantle like Earth. And then in terms of geologic activity, Venus has ongoing tectonics and volcanism. So very similar to Earth in a lot of ways, and yet it's a completely different planet. It is very hot climate-wise. It has much higher atmospheric pressure, sulfuric acid rain, certainly not a place that's habitable or where we expect to find microbial life. So if that is your motivation for studying other planets, then Venus is not high on the priority list in our solar system. But the atmosphere is different, the surface is different. Even though the surface is active, it's a very different style of activity. And the interior is also very different. No core dynamo at the present. Maybe something like stagnant lid convection instead of plate tectonics. So why? How did this end up happening? That's and the argument that I would make is we can learn a lot about our own planet by studying other terrestrial bodies in the solar system, Venus chief among them. So like I said, we've been looking for exoplanets around other stars, and you can plot them in a phase space of orbital period versus planet mass. And we're really starting to get to planets that are comparable to Earth. But if you put Venus on this plot, it's closer to Earth than any other planet that we currently know of. So there's a little bit of observation bias here, of course, that it's easier to see the bodies that have lower orbital periods and higher planet masses. But and so, yeah, we expect there to be plenty of Earth analog planets. And when we do find an Earth analog planet, is it going to be more like Earth or more like Venus? And which is more common, and what makes it be one versus the other is a very important question. So in terms of topography, we see Earth on the right, bimodal hypsometry, where you have the land is above sea level, and then most of the ocean is a few kilometers below sea level. On Venus, you see something a little bit similar, where you have these regions that look kind of like continents, high terrain, and then about 80% of the planet is within a kilometer of the mean radius of the planet. So a lot of flat lowlands, and then these continent-like features that stick above that we call either terras or regios. And the difference between Earth and Venus tectonically, at least in a simplistic sense, is one of a mobile lid versus a stagnant lid. So on Earth, we have this system of plate tectonics that we're all familiar with, where you're driven by the forces of the negative buoyancy of a slab. This is slab pull. There's the, even when the slab is not physically connected, there's an entrainment of the rest of the slab as you have lower portions of the slab that break off. And that's one of the strongest forces driving plate tectonics. There's also ridge push and tractions at the base of the lithosphere. And then on Venus, it's something currently not very mobile, and you just have these tractions acting on the base of the lithosphere for the most part. So this is kind of the two end member scenarios that we think of when we're looking at Earth versus Venus. And so maybe there are two types of Earth-like planets, one that's Earth type, one that's Venus type. To investigate this, we want to know what's going on underground. And this is where geophysics comes in. So let's talk about that. How do we know what's underground on Venus. So some of the story behind this goes back to the mid-1800s and the Great Trigonometrical Survey. There was an ambitious effort to map the subcontinent of India, and you do this through surveying with triangulation and these survey methods that that explore the whole continent. And you do this triangulation so that you come at a point from different directions, and presumably they're consistent. They were having trouble with getting these to be consistent in the north of India. And they brought in someone named John Henry Pratt, who is an amateur mathematician, to try to solve this. And they eventually figured out that the plumb lines were acting up, that when you are surveying, you assume that the plumb lines are going to be vertical, and they were not, that you can explain these inconsistencies if the plumb lines are being deflected toward the Himalayan mountains. And so John Henry Pratt came along and said, aha, Sir Isaac Newton has his law of gravitation. And if you have mountains, that's a lot of mass right there. Therefore, if you drop one of Newton's apples closer to a mountain range, the gravitational attraction of the mountain range will deflect the trajectory of the free-falling apple a little bit. So he applied that back to this problem and did some calculations. We know the density of rocks. We can estimate the volume of the mountains. And he came up with a number that was less than he came up with this large theoretical deflection, which was actually more than the observed deflection that we needed to resolve these inconsistencies. And so why might that be? Is the actual density of the Himalayan mountains, more like the density of water ice? Because it was something like that you would have needed. And it turns out that the answer to this is what we call isostasy, that whenever you have a big plateau with a lot of mass, it needs to be supported by buoyancy underground. And one of the common forms of isostasy illustrated here was actually formulated by a different person, George Airy. And this is the idea that as you have elevated terrain, you need a deep root of crust that supports the terrain, kind of like how the tip of an iceberg is supported by a thick root of buoyant ice underwater. This is something that this idea of using the gravitational attraction of the terrain and the crust of a planet is something that we can apply to space. So the basic idea, if you are tracking an interplanetary spacecraft, we track with Doppler radar, and if you are moving away from Earth, then there's a redshift, a Doppler shift in the radio signal. If you're moving towards Earth, there's a blue shift, and this is the Doppler effect. If you hear a car zooming by, it changes its pitch as it goes as it goes past you. That's the same Doppler effect that we see with radio communication of spacecrafts, and you can use that to work out velocities. Use the velocities to work out accelerations, and accelerations are driven by differences in mass. So here's a more sophisticated way to measure the gravity field of a planet. This is illustrating the Grail mission to the moon. So there was an analog to this on Earth called the Grace and Grace follow-on. And the idea is you have two spacecrafts that are following each other across a planet. And as the first one approaches a mountain range, it accelerates because of the gravitational attraction of that mountain range. And then as the second one catches up, it closes the gap between those two spacecrafts. And so these spacecrafts are constantly measuring the the range rate between themselves, and then communicating with Earth as well. And this is, I'll show this one more time. Pay attention to the length that's changing. So as the first one approaches the mountain, that spacing between the two increases. So this is essentially like measuring the local gravity gradient. If the lead one is experiencing a different gravity than the trailing one. So yeah, let's think about what this means for the gravity field. If we do measure the gravity field, which is the very subtle changes in the strength of gravity across a planet, what do we expect in different scenarios? So the first scenario is isostasy, like what John Pratt and George Airy hypothesized. This idea of an iceberg where from the Archimedes principle, you have the mass of the ice above water is supported by a mass deficit underwater. So if that's the case, you have almost an equal and opposite mass dipole, where there's excess mass at the top and then a deficit of mass that has the opposite sign. And the gravity from those almost completely cancel out. Stronger gravity is coming from the surface topography, weaker gravity is coming from the root. However, the spacecraft is a little bit closer to the surface topography than it is to the root. And so the sum of those contributions, you end up with a slightly positive gravity signal. So if you have the same surface topography that is being supported deeper underground, you have dynamic topography from a mantle plume. The way that it supports the topography is a little bit more complex and has to do with Stokes flow, but it's more or less the same equal and opposite mass anomaly, except now you're much farther away. And so the contribution from the mass deficit is much weaker, and you end up with a more positive gravity anomaly. And so the depth of compensation is almost proportional to the amplitude of the gravity signal that we see. And then one last scenario that I'll come back to in a little bit is the idea of what you would see on Earth. If you have a low viscosity asthenosphere, you can have all sorts that decouples the deep mantle flow from the surface. You can have all sorts of mass anomalies in the lower mantle, and that won't affect the dynamic topography of the surface. And so you can get gravity that is somewhat uncorrelated with surface topography. Now, yeah, so on Earth, that's something that we see, gravity that's somewhat uncorrelated with surface topography at long wavelengths. And yet, if we look at Venus, there's a strong long wavelength correlation between topography and the geoid. So everywhere you see a continent, pretty much everywhere, there's a geoid high that corresponds to it. And so this tells us something about the viscosity profile of the mantle. If you have, so Beta Regio, this is one area in Atla where we have volcanic rises that may be supported by mantle plumes. We have the equatorial highlands, we have Ishtar Terra. We all have geoid highs. If you take every point on these two maps and plot them with topography on the x-axis and geoid on the y-axis and make a big scatter plot, that's what this plot is. And this illustrates something that I think is an important point for what is going to come in the next slides, which is that there is this, there are these trends correlating topography to the geoid, and there are some trends with different slopes. So a lot of the terrains have something that's closer to this shallow slope, this GTR, the geoid to topography ratio. And then other areas and the planet as a whole tends to have this steeper slope. And this is corresponding to that idea that I was describing before, where if you have isostasy, crustal isostasy, it is that shallower slope. And then if you have something more like dynamic topography, then it is a steeper trend. So the ratio between the geoid in the topography is also wavelength dependent. So this is a little bit of a simplification, but this is the basic idea that if you have crustal compensation, it is a shallower slope, and dynamic topography has a steeper slope. So we can deconvolve the contributions from these if we are trying to reproduce the observed gravity field and also explain the normal stresses that would be needed to support the weight of surface topography. We can do an inversion with spherical harmonics. Just very briefly, I'm not going to describe this in great detail, but this is a set of orthogonal basis functions on a sphere, kind of like if you have a Fourier transform with sines and cosines, the same way that you can use sines and cosines to make an arbitrary 1D time series, you can use spherical harmonics to make an arbitrary spherical map. And this is useful because each spherical harmonic is part of a solution to Laplace's equation, which is how gravity propagates through space. So when we do that, we can deconvolve the portion of the gravity field that is corresponding to crustal thickness variations and come up with a map of the thickness of the crust. And if you remember back to the topography map, the topography map looks very similar to the crustal thickness map. Everywhere where there's a continent, so to speak, we have thicker crust. More so in these two continents. Some of the other ones, it's not quite as thick crust compared to what we see in topography. But we have Ishtar Terra is this one up at the top, and then Avda Regio down here at the equator. So along with this, this is a simulation of the view from, if you're looking up at the underside of the crust from the mantle, what would the roots of these terrains look like? So this one is Ishtar Terra in the north. This is the equatorial region in the Avda Regio. So along with this, we can also solve for the mass anomalies in the mantle. So again, you can see Ishtar Terra here, but there are a lot more features that look like mantle plumes. And what we see here is the mass deficit in a column. So kilograms per square meter. And this is like if you take density contrast and you integrate that over a column throughout the mantle. How much deficit of mass, which is red, or excess mass, blue, do we see in different parts of the mantle? And so a mantle plume is one way to think about this, but I want to talk about that in more detail. How do we interpret this map here in terms of, we see mass deficit, mass excess in different places in the mantle on Venus. And there may be two ways that we can think about this. One is with mantle plumes, where you have hot mantle material that is rising. And if material is hot, then it's thermally expanded and there's a density reduction. Another way that you can get density variations is if you have compositional variations. And one source of compositional variation is cratonic lithosphere, where you have very depleted mantle material, depleted in the sense of it's the residuum after a lot of melting, and that reduces the density. So some of the oldest terrains on Earth have what we call cratons, and these could be a source of compositional variation in the mantle as well. And so we see from numerical simulations that this cratonic material is, we know that it's more rigid than the rest of the mantle, and so it accumulates into these masses that build up over time. And this might be very important for plate tectonics on Earth. So there's this idea of a tectosphere that was a more popular term a few decades ago, but the idea of these rigid sections of the mantle lithosphere, and in many cases, these may comprise the majority of the strength of a plate. And so when we think about plate tectonics, we see the crust, but in a certain sense, the crust is maybe just going along for the ride as these lithospheric keels are the real strength of the plates that come together and move apart in the supercontinent cycle. So this may be an important part of explaining plate tectonics versus a stagnant lid. Now on Earth, this is a map of the geoid on Earth, and I don't know if any of you are familiar with have looked at cratons on Earth. I'm curious if you can point out where on this map the cratons are. So there are some that we're more familiar with, like the Canadian Shield. I showed one in Australia. Cratons are around here. And notice the trend with the geoid. There isn't really a trend. We don't see cratons in the gravity field. And this is related to something that was called the isopycnic hypothesis, that it's true that cratons are chemically depleted, which should lead to a higher geoid signal, but they're also relatively cold, which leads to a lower geoid. And these things, on average across the globe, tend to cancel out. Now on Venus, like I said, we see mantle plumes, things that look like mantle plumes, and there's lots of volcanism associated with them. It makes sense that these are mantle plumes, but other areas are not so clear. Like under Ishtar-Terra, this is not, when we look at the surface, it's not obvious that this is a mantle plume. So what is the reason that you would get a big mass deficit in the mantle? And it could be that on Venus, we see something a little bit different, that unlike the isopycnic hypothesis, you have the geoid contribution of the chemically depleted composition outweighing any temperature anomalies that are there. And then there's a net positive geoid signal associated with cratonic lithosphere on Venus, maybe. And this is something that when we look at the correlation between the mantle map and the crustal thickness, at sufficiently high spherical harmonic degrees, they are uncorrelated. They seem to be almost independent of each other. But then there's this longer wavelength range where they seem to correlate with each other. So wherever you have thicker crust, which is to the right on this plot, you seem to have a deficit of mass. So almost all the major continents are in the lower right quadrant of this map. And it's more or less what you would expect if you have a melt fraction of 10%, where the volume of the crust that we see is matched by the mass deficit in the mantle produced by melting. And so that either could be in situ melting, or something that has been proposed for Western Ishtar-Terra is this idea of convergent flow, where you accumulate this low density mantle residuum underneath the plateau. So I want to bring this back to the idea of the comparison to Earth. We talked about plate tectonics and a stagnant lid regime. Should we be thinking of Earth and Venus as these two type examples of these paradigms? Maybe not. So these are simulations of long-term surface mobility of Venus, and one thing that's predicted is this episodic yo-yo state where it's a mobile surface and then it becomes a stagnant lid and then mobile surface. And eventually, in the long term, this becomes a permanently stagnant lid planet. But at least early in its evolution, there's mobility and then immobility on planets that we expect to see. And then on the flip side, when we look at Earth, we might take for granted that Earth has always had plate tectonics. Certainly, it does today, and we see lots of geologic indicators today of things like seafloor spreading, subduction, and collision. But people have noticed that there's a whole there are whole large chunks of Earth history where we see no evidence at all of plate tectonics. This is a paper arguing for something that is a style of tectonics that maybe is more consistent with something that is more like a stagnant lid. And so it's possible that Earth has similarly been in, not always been the way it is today tectonically. So, and going back to Venus, the idea of a stagnant lid, that might be the wrong term because it's not stagnant. We see evidence of tectonic activity, not huge lateral translations of plates, but we do see some block rotation. This is a paper by Paul Byrne looking at blocks that exhibit some rotational deformation and potentially driven by the tractions of the mantle. We don't see subduction properly on Venus, but we do see something that looks like subduction. And there are tank experiments of coronae. I haven't talked about coronae. So this is a corona is means crown, and this is a description of a tectonic feature on Venus that we see nowhere else in the solar system, arguably. And how these form is still a matter of debate, but certainly related to small scale, either upwellings or downwellings, maybe both. And in some cases, we see something that looks like subduction on the periphery of a corona. This is Quetzalcoatl corona, I think. And we see a trench that looks very much like a subduction trench that we would see on Earth. And this is something that is predicted in some tank experiments and numerical simulations. Master's thesis by Rutger Dame looked into the gravity gradients of these profiles across these subduction sort of trenches and found signals that were comparable to what we see on Earth. But on Earth, the solution for the density of the slab shows a much stronger contrast. And so maybe the idea is that subduction tries to start at these coronae, and you have a little slab that doesn't have so much of the slab pull for a couple of reasons, because there's not as much of a temperature contrast. So it's not a cold slab like we have on Earth that's negatively buoyant. And the eclogite phase transition is also deeper on Venus. And that's something that probably drives the slab pull that we see on Earth. And so, so that's why these perhaps never really get started into true, what we think of as subduction. Yeah, stagnant is also the wrong word because this is some work that is in progress with Sydney Briggs at University of Georgia, looking at valley networks where we see them paradoxically going downhill and uphill, and that could be from some combination of tectonics that happen after the formation of the valley or dynamic topography. When we subtract dynamic topography from the terrain, we see a much reduced change in the slope of topography. So that could imply that either tectonically or in terms of dynamic topography or both, Venus is more active than we might think. And then one of the big results from a year and a half ago was the discovery of volcanic flows from old Magellan data. So going back and reanalyzing the radar data and arguing that there has, in the short amount of time between successive flybys of the Magellan spacecraft, there is an eruption. So this is something that hopefully we'll see in the data of the upcoming Veritas and Envision missions that are bringing radars back to Venus. And so we're excited about that. So maybe Venus and Earth are not type and member examples of plate tectonics and stagnant lids, and it's more appropriate to think of them as being on a spectrum of the ways that tectonic bodies operate, and we can expect to find some hybrids of Venus and Earth throughout the galaxy. Now, I'll end with a pitch that if there are any undergrads in the audience, I'm not sure if there are, but we are always on the lookout for qualified PhD students to join us. So this is our group at Baylor University. And we are moving into a newly constructed lab space. I am speaking to you today with a little bit of a sore back because I've been moving furniture all week, but we've got some grad students, some undergrads, and with the faculty, I collaborate closely with Emmanuel Jinju, who is a geodynamicist, and Kat Ross, who earned her PhD here a couple of years ago. So if you're an undergraduate, you could end up here. If you are a PhD student, you could end up here. Yeah, we're doing a wide range of interesting work. This is our PhD student, Nick Wagner, who just graduated and is now at Brown University, doing analysis of seasonal changes in ice cap loads and what that means for deformation of the lithosphere of Mars. And this is data from crossovers of the Mars orbiter laser altimeter. I have another student who is looking at Europa and trying to build machine learning models to understand the line of sight gravity accelerations that we would expect to see in different types of seafloor topography. So training it with lots and lots of synthetic data with different parameters and different seafloor depths, different types of topography, and different noise contribution to the data. And our hope is that by the time Europa Clipper gets to Europa, that we will be able to use that to, as accurately as possible, characterize the interior structure of Europa. We are applying these sort of gravity methods that I talked about to the moon, where we have excellent gravity data. This is an example of some apparently silicic domes on the moon, and our undergrad LA North has been looking at the bulk density of the domes, and with gravity data confirming that it is much lower density than some of the other terrains that we see, and perhaps even corresponding to things like granitic intrusions in the mid-crust. And these are going to be the sites of, I talked about CLIPS missions at the beginning, which is commercial lunar payload services. So these are, this is a program where NASA is giving contracts to private spaceflight companies to send instrument payloads to the moon. And one of the upcoming payloads will be going to, I think, Gamma Dome. And so we're excited to connect orbital observations to what we see on the ground. Venus doesn't have a lot of craters. I didn't talk about that part of it, but that is in part because of the thick atmosphere. We see a drop off. The most common crater is something around 10 kilometers diameter, and you have the thick atmosphere that's filtering out the smaller impactors. And we have a project looking at the trajectory of impactors through a thick atmosphere, and does that actually match the atmospheric filter that is recorded in the distribution of craters that are on the surface. There are different kinds of gravity analyses that you can do and different assumptions that you can make. And Isabella Hampton is a PhD student who is looking at the possibility of different mafic contents of different features and what that means for crustal thickness. And this is important because it's hard to imagine, it's very hot inside Venus. And if you have a root that's too deep, then it would relax. And so we infer heat flow and the thermal evolution of Venus. We can constrain that by the existence of continents, basically. Why hasn't everything just relaxed away like molasses? And this is part of understanding that problem. And then we do some terrestrial crater field work as well. So we did a survey at a gravity survey at Meteor Crater. This is in revision at JDR Planets, and another survey at Kentland Crater in Indiana. This is us deploying the magnetotellurics, that method that's going to the moon. So we have bold ambitions to apply this to the moon, and this could be you on the right, bringing your geophysical instrumentation to the moon and learning what we can. This is one forward model of what we expect from gravity if there are ice deposits in permanently shadowed regions, different scenarios of pore filling versus silicate displacing. But there's a lot of science to be done on the moon, and that is seeming like a greater possibility than it did even 5 years ago. And so we have exciting times coming up in the next few decades. All right, so that's actually the end. Thank you.
Questions for Peter?
A great talk, Peter. Thank you. I've always, it's always Mars with me. So I was always wondering if you could look, we have there's a scaling rate for transitions and craters from simple to complex, and it's based upon planetary gravity, right?
Yeah.
And on Mars, it's kind of hard to tell because you usually have infill that covers the transition, whether you have peak ring or not. But would it ever be a way to look at the transition between simple and complex craters and back out a gravity field that would give you some insight into the Martian subsurface, looking kind of like a metadata analysis of simple to complex crater transitions on Mars? Or is that so far out of resolution of the data set we have that you couldn't back out anything useful?
Absolutely. So there are studies that have looked statistically on the moon, because we have so many craters that are within the resolution limits of the GRAIL data set. And so we see very clear trends in the Bouguer anomaly of a crater, the profile of a crater for different sizes. And we can very clearly see transitions where the MOHO starts to be uplifted, where you start to transition between creation of porosity versus the destruction of porosity. And so there are there's a lot of analysis that is still being done with GRAIL data to look at the transitions in cratering styles and mechanisms of cratering. And on Mars, we don't have nearly as good resolution gravity data as for the moon. And we never will probably because on planets with an atmosphere, you can only get so close. And the resolution of a gravity field that you can get from orbit, at least, is dependent on the altitude of.
I'm all for a Grail Mars mission. Put something in the
Yeah.
Lagrange point and do a Grail mission to Mars.
Yeah, so if you sent Grail to Mars, it would have to be at a higher altitude to be above the atmosphere. And so the end result would not be quite as high resolution, but you have an atmosphere and you have deposition. We know that there's deposition of ice at the poles, and so that you could track atmospheric processes and transport of water as well. Yeah, yeah, I think that's Maria Zuber's next priority, that thinking that if we're going to send Grail to another planet, it should be Mars.
Thank you.
Hi, thank you for the talk. I was wondering if you saw any correlation with like age with the anomalies that you had, like if they're like kind of less stark or kind of more pronounced.
On Venus?
Yeah, Venus.
We don't know so much about age. That is another open question. So back when Magellan went to Venus in the early 90s, they saw, so there are about 900 craters in total. That's much fewer than on the moon. You have millions of craters. And Mars has more craters as well than Venus. And that's one of the main ways that we put ages on planetary surfaces. If a surface has been sitting there for a longer period of time, it will have accumulated more craters. But when there's only 900 over the whole surface of the planet, it is harder to do those statistics. So when Magellan first arrived in the early 90s, they saw what was almost indistinguishable from what is indistinguishable from a random distribution of craters. And so one of the early conclusions was that the entire surface of Venus is all the same age, and maybe there was a catastrophic resurfacing event that, just reworked the entire surface of the planet. And then subsequent studies were looking at, well, that's one interpretation, but if you have patchwork resurfacing, maybe some smaller areas are younger or older, and we wouldn't necessarily be able to tell that. The thought is that some of the tessera terrains are probably the oldest regions, and those regions do have much more of the crustal thickening than the mantle. So it does seem like the younger regions do have more of a deep mantle buoyancy component, and the older regions are just crustal thickening.
Oh, sorry.
Hi, enjoyed the talk. When you're talking about the corona, are they circular features?
Yes.
So I guess two questions. One, could you give a sense for the scale of them? You talked a little about, there was a diagram of the process, which I think I sort of picked up on. And when you said that they don't end up subducting, is it, I think of subduction as relatively like a linear thing that happens along the line. Like, how could you subduct a circle into itself?
Yeah, that's the geometry doesn't quite work. And so it starts and then it doesn't really take off is the answer. So the scale, the largest corona is this one right here. So it's large enough that we can see it in the topography. And then you have some smaller ones. Here's one that you can see. You can see little, I don't know how well you can see the screen, but there are a lot of them. Most of them are smaller than what you can see at this scale. Yeah, and we don't know a whole lot about how subduction initiates on Earth. And so presumably on Earth, you would have something similar where it's something that you don't start off from from scratch and then develop an entire chain of, or a big long trench that, you know, spans the hemisphere. You start off with something smaller, with something localized, and then it propagates, maybe they connect, and you get something that looks more like a subduction zone. But that process does not take off on Venus.
Thanks.
What's the question in the chat? So Chao Yang Zhang, sorry if I butchered that, asks, he's got two questions. First question is, in one of the plots, the one with different trends, you mentioned one is isostasy and another is dynamic topography. Do we empirically decide which model to use to separate those two contributions, or do we have some other ways to separate the contribution of isostasy and dynamic topography?
It's an evenly posed problem because we have, at every point on the planet, we have two constraints. We have the gravity, and we have the height of topography, and the amount of normal stress that you need to support the weight of that topography. And so from that, we can solve for two things about the interior of the planet. And I choose those two things to be the thickness of the crust and the buoyancy of the mantle. And so that has baked into it an assumption that all topography is compensated. And on Mars or on the moon, that would not necessarily be a good assumption, because the lithosphere can be quite stronger and can support uncompensated topography through the elastic strength of the lithosphere. But it is because we are applying these assumptions that we need to reproduce the observed gravity field, but also to minimize uncompensated stresses.
All right, second question. When you apply line of sight gravity, the line of sight gravity approach outside of Earth, how do you account for non-gravitational force?
Oh, so yeah, there's radiation pressure from the sun that has a slow acceleration on a spacecraft. There's drag if you're dealing with Earth. For the gray satellites, I think they have internal accelerometers as well, which gives you a sense of atmospheric drag. But yeah, there's a lot that goes into that, and that's the engineer's job. I don't do that.
Any other questions?
I have a question. Following up on the Venus and the gravity questions. For the upcoming missions for Venus, will they be able to provide a gravity field that will be able to address some of these issues with subduction, corona, et cetera?
Oh yeah. So the current resolution of the gravity field is so spherical harmonic degree 90, if I remember correctly, is something like 200-kilometer horizontal length scale. So anything smaller than that, we can't really resolve or study with gravity. And that is right at the scale of some really interesting processes like the coronae. And in order to study those better, so another thing with the Grail data on the moon, that has been great in terms of solving for the bulk density of the terrain, which is something, one of these projects that we are working on, because we can use the really high pass, short wavelength data of the gravity field to isolate the density of shallow structures. And so the higher resolution, even if we go just a little bit better resolution in the gravity field on Venus, that's one of the things that we can potentially do. We can start to put gravitational estimates of the density of some of these terrains that we see.
Any other questions? Okay, well, let's thank Peter again. There's coordinating lunch at noon. I think there's quite a few graduate students who have signed up for that. And then, yeah, thanks again.
Thank you.